Hello. In this video, we're going to discuss directional derivatives and consequences of the definition. The- Let's recall what that definition is and how we compute a directional derivative. So the directional derivative of f at the point AB in the direction of the unit vector u is defined by this symbol, capital D and the subscript u for the vector f at your point AB. We're just focusing on two variables in this situation so far, is defined by the following. So what we do is we take the function f, we restrict it to a line passing through the point AB when t is equal 0 in the direction of the vector u. So if we think about u as your compass reading for two variable functions. All right, so that's where you're setting your compass. If you think about the graph of this function being a mountainside, you want to know, are you going to be going uphill or downhill when you move in the direction of u from the point AB? That's what the directional derivative will tell you. Now how we compute it, right, we have to use the chain rule. We're going to take the derivative of this composition and then plug in t equals 0. So by the chain rule, it's the derivative of the outside function, which is the gradient of f, evaluated at the inside, dotted with the derivative of the inside function. And the derivative of this expression, this vector valued function with respect to t, is just u. Now we plug in t equals 0. That doesn't change u, that's a fixed constant vector. That's going to wipe this part out and we're just going to be left with AB. So the directional derivative is just computed by taking the gradient, plugging in your point, and then dotting it with your given unit vector. So that's an important factor we're going to use a lot. The directional derivative can be computed with this simple dot product, where again the gradient is just, in the two variable case, is where you have the partial derivative with respect to x in your first coordinate, and partial derivative with respect to y in your second coordinate. The same result holds for functions of three variables or more. The directional derivative is defined for a unit vector pointing in the direction of a unit vector. It's defined and computed in the same exact way. We find some curve passing through the point we're focusing on in the direction that we're tending to go at a particular time. The easiest types of curves are lines, and we can easily cook up a line passing through the point we're focusing on when t is equal to 0, and we define our directional derivative to be that derivative evaluated at t equals 0 when we're at that point in question, and that, by a similar calculation up above using the chain rule, gives us this dot product. Okay. All right, now we're going to focus a little bit on the geometric interpretation of the directional derivatives for two variable functions. We lose our geometric interpretation for functions of three variables and greater. What it represents is the slope of the surface at the given point in the given direction. All right, and it's key that u is a unit vector here. All right, if u is not a unit vector, then the dot product grad f dot u only represents a slope when u is a unit vector. If that u was not a unit vector, that would not represent the slope to the graph of your function. All right, if it's not, if you're given some other direction vector, say by given a vector a, we can always normalize that to create a unit vector. Okay, let's look at this picture on a graph. Okay, so here I'm using Paul Seeberger's applet CalcPlot 3D. So we've got the plot of our two variable function here. Now by moving the point over here on the left hand side, I can get to a different spot on the graph of this function. I'm just going to stop it there. All right, now we can also move the direction we're pointing in. All right, so if we look at rotating the figure around a little bit, the blue is the slope of the tangent line and therefore the slope of the surface. If we rotate the direction we're pointing in, then that certainly changes the slope of that line. So it definitely matters which direction we're pointing in as far as what our slope is going to be, whether we're going up the line or down the line. So our slope could be positive if we're, for instance, moving in this direction, or negative if we're moving in this direction. But that certainly matters. At a given point on your surface, it's going to make a difference which direction your compass is pointing in to determine whether you're going to be going uphill or whether you're going to be going downhill from your given point. Alright, now for three variable functions, again, we lose the geometric interpretation, but we can still think about that directional derivative as an instantaneous rate of change. Some other important facts about directional derivatives. It turns out that the gradient points in the direction of greatest increase for the function f. Its opposite, the negative gradient, points in the direction of greatest decrease. Again, let's try to look at this graphically. So for this, what we're going to do is put the gradient vector into the graph. Now, on this graph, we can see we have this local maximum right here. We've got this relative maximum. As I move the point in the xy plane, you're going to see below it the gradient vector. Right? We think about the gradient vector as something in 2D. Notice as we get away from the hillside there, the gradient vector is pointing in towards it. Right? The gradient vector plotted in the xy plane is pointing towards the increase in f, pointing towards the mountaintop here, if you will. So it's pointing towards the direction of biggest increase. What about over here at this trough point, at this low point? Well, if we go over into what's really the fourth quadrant in the xy plane, we see the gradient vector is pointing away. Now, the reason it's pointing out is because at that low point, we're trying to point in the direction of biggest increase for f. Increasing is going to make us go up and out of this valley on the graph. Okay. Another way to look at this is by looking at the contour plot. Okay. All right, here's a picture of that contour plot for that same function. We can still move the gradient vector around, and notice in the first quadrant our gradient vector is pointing towards the increase in f, the greatest increase. Over here in the fourth quadrant, it's pointing also towards the greatest increase, but this is the low point we're trying to, in the middle here we have the low point, and it's pointing in a direction that will make us climb out from that low point. Okay, now why is that the case that the gradient points in the direction of greatest increase? We can see that by, and we'll focus on the two variable case again, the similar results hold for functions of three variables and more. Assuming the gradient vector is non-zero, then the directional derivative is given by this dot product. We know another way to compute the dot product, and that's by taking the length of each vector and multiplying it by the cosine of the angle in between. Now the length of the vector u is 1, so that can be gotten rid of. So the directional derivative is really given by this quantity, the length of the gradient vector times the cosine of the angle in between your unit vector and the gradient vector. Now the cosine function will be maximized at 1 when theta is 0, minimized at -1 when theta is pi. So what does that tell us? This will happen, theta will be 0 when the vector grad f and u point in the same direction. It'll be minimized when theta is pi, and that's going to mean that the gradient of f and u point in opposite directions. So what's our conclusions? The maximum value for the directional derivative will be the length of the gradient, and that's going to occur precisely when u and gradient of u point in the same direction, or equivalently when u is given by this corresponding unit vector. Similar statement can be made for the minimum value. The minimum value will be when the cosine is -1, and therefore the directional derivative's minimum value is the opposite or the negative of the length of the gradient, and that's going to occur when u is pointing opposite the gradient vector, or equivalently when u is this unit vector, the negative gradient over its own length. Lastly, we didn't say this above, if the gradient vector is 0, then the directional derivative has to be constantly 0. So it doesn't matter what unit vector you pick, your directional derivative will be precisely 0. Okay. Again, we did see this looking at this contour plot here. The directional derivative is pointing in the direction of largest increase, or always pointing in the direction of largest increase. Its opposite, we don't see that in the figure, but that would point in the opposite direction, would point in the direction of largest decrease. Okay. All right, the last um, conclusion we're going to make is something about level curves. Okay, so it turns out that the gradient for two variable functions, the gradient is perpendicular or normal to level curves. Now, why is that the case? All right, if you parameterize your given level curve by, say, r of t, so the level curve is f of xy equals a fixed constant, then you're going to have f of r of t equals that fixed constant. If you differentiate both sides with respect to t, the derivative of the right hand side will be 0. We have to use the chain rule on the left hand side, and it's the gradient of f evaluated at the inside function dotted with the derivative of the inside function. Well, we know that this vector will be tangent to the level curve, and therefore that forces this other vector, the gradient, to be perpendicular to the level curve, which we're describing by r of t. Okay, we can also see this last fact geometrically. All of these contours here are representing level curves to the surface. So if you fixed your z height, we're talking about a level curve. We intersect, for instance, the plane z equals 1.8 with this surface, we're going to get these two curves. All right. Now that represents a curve down in the xy plane, and we can see as we move the gradient vector around, it will be perpendicular to one of these level curves.